So I am Ajit Khaparde. I work on the Broadcom NICs. Since 2015, I've been working on the DPDK drivers. And a couple of years back, there was this presentation from NVIDIA with Mellanox at that time, which showed how to actually get the GPUs to work with NIC or GPUDirect to work with a NIC in DPDK environment. And I've been trying to see if the Broadcom NICs can actually do the same thing. So finally, I got my chance a few months ago, and I thought, okay, let's put this together and share it with everyone on what we did. So that's where we are. So before I jump to what we did, let's quickly go over what GPUDirect is. It basically kind of gets coupled with this RDMA, and the term that comes is GPUDirect RDMA. It allows a direct path between a NIC device and a GPU, so that the DMA is possible directly from the NIC into the GPU buffers. Typically, without that, you would probably need a staging buffer to hold the data intermediate and then copy it over to the GPU. And it has been working fine with RDMA, Rocky and InfiniBand kind of deployments, and there are like all these already used and those kind of NCCL applications taking advantage of that. And then NVIDIA and Mellanox proved that this is possible using DPDK. So this is how, where it started. It was in the DPDK summit where this topic kind of came up, and NVIDIA and Mellanox put together this sample application, modified sample application, which allowed them to prove this concept. And later on, the GPU dev library was added, and then an application GDR copy clubbed along with that gave the solution. So what I thought I needed was some changes to the sample application that NVIDIA and Mellanox had put together. I called it the L2 forward NV BRCM. And I had to make few changes to the application. So I retained the NV and added the Broadcom flavor to it. And then to get this solution to work, I had to make a couple of changes, not only to the DPDK library, but to the GDR copy sources also. So this kind of just gives a very rough idea of some of the pieces, especially keeping in view the DPDK application that we spoke about. The key pieces here are, since it's NIC driver, we needed the DPDK application to not only perform the NIC operations, like probing the NIC device, allocating the memory, and all that kind of stuff, but also initialize, probe, and allocate memory for the GPU that we are trying to communicate to. The application had different modes, which allowed me to kind of make sure that the packet is actually going to the GPU and doing what it is supposed to do. And not just kind of end up in a black hole, to say. And and as I said, I had to modify some of the layers to kind of get this to work. At the high level, the changes that I had to make, apart from the application, was to in the GDR copy sources, which actually allowed to manage the GPU memory. It also is a glue to between the DPDK library, and then the underlying peer-to-peer peer-mem library drivers that NVIDIA provides. So the kernel driver basically communicates or tracks the peer-mem symbols, which are exported by the peer-mem driver, and then the application, the GDR API, uses ioctls to communicate with the GDR DRV, which is where the addresses which are seen or which are provided or allocated by the application, which happens to be in the unified virtual memory environment that NVIDIA has so conveniently put together, and there is a lot of documentation and literature on that. We managed to get the DMA address, which is actually needed by the NIC in this case for doing this GPUDirect RDMA using DPDK. I modified the Broadcom PMD to support the buffer data split or header data split. That was just to kind of make sure that the payload actually ends up in the designated area where I want, like maybe if I want the payload to actually just arrive in the CPU and the data goes to the GPU. Maybe, I mean, in the real use case, that actually could be your image data. I kind of switched the roles in the Broadcom favor of the application, where the payload went to the CPU and the header went to the GPU, and I actually modified some bits in the header and got the packet out. So sort of to prove what I was doing was actually happening in the GPU. I don't want to spend a whole lot of time over this, but because as I said, there is like good amount of literature out there when you search for this. But this essentially provides unified address space across all the PCI devices, and this is where the CUDA layer initializes and tries to allocate the memory, which is essentially used for putting the data in the GPU. The applications can access this memory depending on how it's actually provided. In this particular case, as I said, the NIC actually was able to DMA the data, but then the application is the one which essentially performs the final set of actions. And when the CUDA initializes, it actually gets either it can get a CUDA managed virtual address or a CPU managed virtual address. So depending on how the application allocates the memory, it can actually either be in CPU managed GPU address mode or GPU address mode. So what I did may not be the perfect way, but at least it kind of got me going. It kind of proved that even the Broadcom NIC, not just the NVIDIA NIC, works in this particular scenario. So just to kind of give an example, when I initialized the application, it kind of was giving me the CUDA allocated memory, as I said, and it was in a certain address space. And essentially, when you look at that, it was not something that I could actually kind of do a DMA, perform a DMA to from a NIC perspective. So this is where like I will briefly go over the change that I made. So the P2P get pages kind of allows to map the memory which was given by the CUDA application, pins it, and then such that you can actually use it for the DMA. And this information was passed down to the kernel driver, the GDR DRV driver that I spoke about, and then the application. These two together, they kind of checked with the peer-mem driver that NVIDIA provides, and gave back the actual DMAable address that I needed to feed into my NIC. then, I mean, the other change that I had to actually make sure was this new API that I added, the GDR copy DMA, that's what I call, because it was then giving me a DMA-able address, was available when the DPDK libraries and application would compile, and if it was not, like written an error. And then as a part of the GPU dev changes, there was an API to map and unmap the allocated memory. And yeah, so at the end of this whole thing, the address which was there at the top kind of got translated to the actual DMA-able address in the range that actually I showed at the bottom. So it took a couple of iterations to go through this, these different layers, but then yeah, once we peeled all this, we were able to actually convert the UVM address into a DMA-able address, and the NIC actually did the DMA to the GPU. Yeah, this is where I kind of like thought, okay, let's kind of like get a little more adventurous. So I modified, made some changes in the CUDA code to swap the MAC address, played with some other information in the packet, but then that's about it. I mean, CUDA is a different beast altogether, and I could not spend time improving that. Moreover, this is like DPDK being a lossy kind of environment. I didn't actually like want to spend time trying to come up with a whole connection management and all that kind of thing to utilize any of the high-end CUDA libraries. But yeah, essentially, it kind of helped me prove that the data was actually going to the GPU. I was able to manipulate it, and then actually, yeah, call it victory.